Good day, everyone. We are the third group to present. I'm Zachary Albert John O. Fernandez, and let us start the presentation with our research study entitled The Effectiveness of Enhalus acoroides as Alternative Compost for Plant Growth. The researchers wanted to conduct this study to know its effectiveness for plant growth and development in comparison with commercial fertilizers that can create a harmful effect if frequently used in our environment.
Background of the study. Analos acorides is a seagrass that are commonly found in the back beach of Bulabog. During low tide and windy days, dead Analos seagrass are brought inland to the shores. As you can see, dead Analos acorides affects the beauty and smell of the beach. To help the community and improve the situation in the beach, our study is aimed to know the effectiveness of Enalus acorides as compost for plant growth. The dead Enalus acorides that are brought inland can be used as compost by the locals to reduce the impact in the beauty of the beach. But why Enalus acorides? When compared to fertilizers, it can help the environment because by using commercial fertilizers, it can 1. Build up chemicals in the soil which in the long time can kill the plants. 2. Rather than saving the environment, you create more trash. 3. Chemical fertilizers can harm the people when consumed or exposed to. Rationale. Enhalus acorides is a seagrass that belongs to the family Hydrocaritaceae, also known as tapegrass. It is widely distributed along the coast of the Indian Ocean and the tropical part of the Western Pacific. Enhalus acorides leaves are 12 to 20 millimeters wide and it is 30 to 150 centimeters tall. The rhizome is 15 centimeters in diameter, branching monopodially when formed. Boracay has an abundance of Enhalus acorides throughout its beaches. Furthermore, our study aims to know the effectivity of the compost that is made of from Enhalus acorides to be used as fertilizer for the development of plant and as an alternative for fertilizers. Statement of the problem. This study would like to determine the effectiveness of Enhalus acorides as an alternative compost for plant growth. To measure the effectiveness, the researchers used mung beans, or commonly called mungo, to measure the plant growth and development. Specifically, this study would like to seek the answers for the following questions. 1. What is the average growth rate of mung bean plants potted in the following types? A. Enhalus acorides alternative compost. B. Commercial fertilizers. C. Soil only. 2. What are the measurements of plant development in Enhalus acorides alternative compost when compared to other treatment groups in terms of A. Number of leaves. B. Leaf area in square centimeters.
I will discuss the materials and methods of this research. The materials that we need in the study were 1 kilogram of Enhalus acoroides, 2.21 kilogram of pot soil, commercial fertilizer, weighing scale, shovel, gloves, mung bean plant seeds, 13 small pots, measuring tape, ruler, scissors, markers, oven, and paper. Next is the method. Collection of sample. Enhalus acoroides samples collected at the seagrass beds from the coast of Bulabog Beach, Barangay Malayaklan. The Enhalus acoroides seagrass are collected by pruning at the base with scissors and stored in a large container or bin. It was collected early in the morning and late afternoon where low tides occur. Next is washing method. The Enhalus acoroides that they collected must wash with clean water to remove the excess salts and sands. Next is preparation of compost. The Enhalus acoroides seagrass, they cut into small pieces and then using an oven, they make dried for 10 minutes. And then, It pulverized using a mortar and pestle. The total of all is 765 grams of dried and pulverized acoroides was gathered.
Ragdoll method. Ragdoll method consists of a rolled tube of moistened paper for containing the seed to be tested for germination. The researcher used ragdoll method to the mung beans that are first tested for germination. The seeds are wrapped in a moist towel for 3 to 4 days. Planting and observation. Each treatment is planted with 3 mung bean seedlings, which it is out-chosen product to experiment in a 3 cm deep hole, and it is watered with a 30 ml water every 7 a.m. in the morning and 5 p.m. in the afternoon. The observing of this treatment conducted from June 6 to June 26 and 447 Zone 5 Balabag, Malay, Aklan. Data collection. Every 7 days, the collecting of data is conducted where we collected the height, leaf count, and leaf area.
Results and discussion. The present study was conducted to determine whether N-Halus acoroides can be used as alternative compost. The experiments were laid out with 5 treatments having 3 replications. The 5 treatments, Treatment A, 100% soil, Treatment B, 75% soil and 25% N-Halus acoroides, Treatment C, 50% soil and 50% N-Halus acoroides, Treatment D, 25% soil and 75% N-Halus acoroides, and Treatment E, 100% soil watered with commercial fertilizer. One-way ANOVA was utilized to determine if significant differences exist between the treatments. Application 1. Plant height. Table 1. The height of mung bean plant from different treatments at different times after sowing from the first replication. The collection of data was conducted every 7 days within a 21-day period where the plant height are collected. Table 2. One-way ANOVA test for plant height of mung bean from different treatments from the first replication. The result shows that there is significant difference in the plant's height in centimeters across 5 treatments. F 4,10 is equal to 5.654 with a p-value of 0.012. Table 2.1. Descriptive of plant height from different treatments from the first replication. 2-case HSD was used as a post-hoc test. It reveals that those plants planted on pot E with a mean of 17 and a standard depth of 3.081 yields the tallest plants. Pot A with a mean of 14.8 and a standard depth of 1.908 was significantly taller than those on pot C, with a mean of 11.433 and a standard depth of 4.12. Also, the plant's height on pot B with a mean of 10.633 and a standard depth of 1.115 are taller than those on pot D with a mean of 8.167 and standard depth of 1.041, which has the shortest plant recorded for the first replication. This finding shows that different treatments affects the plant height. Figure 6. Line graph for means of height from different treatments of the first replication. Number of leaves. Table 3. The number of leaves of mung bean plant from the different treatments at different times after sowing for the first replication. The collection of data was conducted every 7 days within a 21-day period where the number of leaves are collected. Table 4. One-way ANOVA test for number of leaves of mung bean plant from different treatments of the first replication. The result shows that there is no significant difference in the plant's number of leaves across the 5 treatments. F 4, not a number is equal to not a number and the p-value is also equal to not a number. Table 4.1. Descriptives of number of leaves from the different treatments from the first replication. 2 keys HSD was used as a post hoc test. It reveals that there is no significant difference in the plant's number of leaves across the 5 treatments for the first week of recording. Leaf area. Table 5. The leaf area of mung bean plants from the different treatments at different times after sowing for the first replication. The collection of data was conducted every 7 days within a 21-day period where the leaf area are collected. Table 6. A one-way ANOVA test for leaf area in centimeters squared for mung bean from different treatments from the first replication. The results shows that there is significant difference in the plant's leaf area in centimeters squared across the 5 treatments. F, 4, and 10 is equal to 2.090 and the p-value is 0.157. Table 6.1, a descriptive of leaf area from different treatments from the first replication. 2 keys HSD was used as a post-hoc test. It reveals that the plants in pot A with a mean of 5.557 and a standard dev of 1.964 has a larger leaf area than those of pot C with a mean of 3.807 and a standard dev of 3.303. Also, the plant's leaf area from pot A with a mean of 2.667 and a standard dev of 1.486 has a smaller leaf area even though it is taller than pot C. Moreover, plants grown in pot B with a mean of 2.267 and a standard dev of 1.172 has a larger leaf area than pot B with a mean of 1.410 and a standard dev of 0.259, which has the smallest out of the group. This finding shows that the different treatment gave an effect on the plant's leaf area. Figure 7. Line graph for means of leaf area in centimeters squared from different treatments from the first replication. Replication 2. Plant height. Table 7. The height of mung bean plant from the different treatments at different times after sowing from the second replication. The collection of data was conducted every 7 days within a 21-day period where the plant heights are collected. Table 8. A one-way ANOVA test for plant height of mung bean from different treatments for the second replication. The result shows that there is significant difference in the plant's height in centimeters across the 5 treatments. The F value 4 and 10 is equal to 7.921 and the p-value is equal to 0.004. Table 8.1. A descriptives of plant height from different treatments from the second replication. 2 keys HSD was used as a post hoc test. It reveals that those plants planted on pot A with a mean of 19.5 and a standard dev of 1.308 yields the tallest plants. Pot A with a mean of 14.8 and a standard dev of 1.908 and pot B with a mean of 14.8 and a standard dev of 3.005 has the same value for their means but different when it comes to their standard deviation. Next, pot D with a mean of 12.933 and a standard dev of 2.183 develops a more taller than those in the first replication. Lastly, for pot C with a mean of 10.667 and a standard depth of 0.945 gather the shortest record for height. Figure 8. Line graph for means of height from different treatments from the second replication. Number of leaves. Table 9. The number of leaves of mung bean plant from the different treatments at different times after sowing from the second replication. The collection of data was conducted every 7 days within a 21-day period, where the number of leaves are collected. Table 10. A one-way ANOVA test for number of leaves of mung bean plant from different treatments of the second replication. The result shows that there is no significant difference in the number of leaves across the 5 treatments, where the F value is 4 and not a number is equal to not a number, and the P value is also equal to not a number. Table 10.1 Descriptives of number of leaves from different treatments from the second replication. 2-case HSD was used as a post-hoc test. It reveals that there is no significant difference in the plant's number of leaves across the 5 treatments for the second week of gathering data. Table 11. The leaf area of mung bean plants from the different treatments at different times after sowing for the second replication. The collection of data was conducted every 7 days within a 21-day period, where the leaf area are collected. Table 12. A one-way ANOVA test for leaf area in centimeters squared of mung bean from different treatments for the second replication. The result shows that there is no significant difference in the plant's leaf area in centimeters squared across the 5 treatments. F value 4 and 10 is equal to 16.325 with a p-value less than 0.01. Table 12.1, a descriptive of leaf area from different treatments from the second replication. 2-case HSD was used as a post-hoc test. It reveals that the plants in pot E with a mean of 8.133 and a standard depth of 0.551 has a larger leaf area than those on pot D with a mean of 300.843 and a standard depth of 0.596. Also, the plant's leaf area from pot B with a mean of 3.037 and a standard depth of 1.445 is a bigger than pot A with a mean of 2.667 and a standard depth of 1.488. Moreover, plants grown on pot C with a mean of 2.530 and a standard depth of 0.293 as the smallest out of the group. This finding shows that the different treatments gave an effect on the plant's leaf area. Figure 9. A line graph for means of leaf area in centimeters squared for different treatments for the second replication. Replication 3. Plant height. Table 13. The height of mung bean plant from the different treatments at different times after sowing from the third replication. The collection of data was conducted every 7 days within a 21-day period where the plant height are collected. Table 14. One-way ANOVA test for plant height of mung bean from different treatments for the third replication. The result shows that there is significant difference in the plant's height in centimeters across the 5 treatments, where the F value 4 and 10 is equal to 1.492 and the p-value is equal to 0.276. Table 14.1. A descriptives of plant height from different treatments from the third replication. 2-case HSD was used as a post-hoc test. It reveals that pot E with a mean of 18.733 and a standard depth of 1.914 yields the tallest, and pot B with a mean of 15.067 and a standard depth of 3.011 follows. Next, the plant from pot D with a mean of 4.967 and a standard depth of 3.247 are taller than those on pot A with a mean of 14.800 and a standard depth of 1.908. With pot C mean with a mean of 14.467 and a standard depth of 2.079 having the shortest out of the group. Figure 10. A line graph for means of height from different treatments from the third replication. Number of leaves. Table 15. The number of leaves of mung bean plant from the different treatments at different times after sowing from the third replication. The collection of data was conducted every 7 days within a 21-day period, where the number of leaves are collected. Table 16. A one-way ANOVA test for number of leaves of mung bean plants from different treatments of the third replication. The result shows that there is significant differences in the plant's number of leaves across the 5 treatments, with the F value 4 and 10 is equal to 0.583 and a p-value equal to 0.682. Table 16.1. A descriptives of number of leaves from different treatments from the third replication. 2-case HSD was used as a post-hoc test. It reveals that there is significant difference in the plant's number of leaves across the 5 treatments for the third week of gathering data. Pot A with a mean of 3 and a standard dev of 1.732 and Pot B with a mean of 3 and a standard dev of 1.732 shares the same value and leads the group for the number of leaves, followed by Pot D with a mean of 2.667 and a standard dev of 1.155, which has a larger mean value than Pot C with a mean of 2.333 and a standard depth of 0.57, and lastly Pot E with a mean of 1.667 and a standard depth of 0.577. Considering its height, it has the lowest value for the number of leaves computed mean. Figure 11, a line graph for the means of number of leaves from the third replication. Leaf area, Table 17. The leaf area of mung bean plant from the different treatments at different times after sowing for the third replication. The collection of data was conducted every 7 days within a 21-day period, where the leaf area are collected. Table 18. A one-way ANOVA test for a leaf area in centimeters squared of mung bean from different treatments for the third replication. The result shows that there is significant difference in a plant's leaf area in centimeters squared across the 5 treatments, where the F value 4 and 10 is equal to 0.573 and a p-value equal to 0.688. Table 18.1, a descriptive of leaf area from different treatments for the third replication. 2-case HSD was used as a post-hoc test. It reveals that the plants in Pot D with a mean of 5.400 and a standard depth of 3.280 has a larger leaf area than those on Pot B with a mean of 4.173 and a standard depth of 3.087. Also, the plant's leaf area from Pot A with a mean of 2.667 and a standard depth of 1.488 has a smaller leaf area even though it is taller than Pot C with a mean of 3.973 and a standard depth of 1.263. Moreover, plants grown in Pot E with a mean of 3.580 and a standard depth of 1.282 has a larger leaf area than Pot A, which has the smallest out of the group. This finding shows that the different treatments gave an effect on the plant's leaf area. Figure 12, a line graph for means of leaf area in centimeters squared from different treatments for the third replication.
Conclusion. In general, the researchers concluded that the plant growth under commercial fertilizer had a faster growth rate than any other treatments. But as week goes by, it greatly affects the plant's leaf count and area. The researchers also concluded that plants potted in soil only grew earlier, but it is then pushed back by the Enalus acridis alternative compost treatment in the later parts of the experiment. In conclusion, the Enalus acridis alternative compost shows an increase on height, number of leaves, and leaf area when compared to soil only. Enalus acridis does not beat commercial fertilizers. However, it can be used as an alternative compost to plants. Recommendations. Based on the findings and conclusion in the study, the following recommendations are suggested. 1. The method used in making the compost in this study utilizes an oven to produce. Another method by making the compost is through natural decomposition of the Enalus acridis on soil for 30 days. 2. More research studies should be conducted to validate and verify the effectiveness of Enalus acridis as an alternative compost for plant growth. First and foremost, praises and thanks to the God, the Almighty, for His showers of blessing throughout our research paper to complete the research successfully. We would like to give thanks to the panelists who gave recommendations and suggestions to further improve our study. We would also like to give our greatest gratitude to our research advisor, Mr. Luther G. Kapispisan, for his guidance and knowledge, and we are thankful for our school principal, Mr. Eliseo B. Kasidsid, for letting us pursue this research study. We are extremely grateful to our parents for their love, prayers, advice, and encouragement, and to our classmates who also helped us in the making of our research.